asymmetry. So let me remind you what the problem was, that we know that today in the universe there is more baryon than antibaryon. Okay, we know there are protons but no antiprotons. And the question is, how is this asymmetry generated? Now, one thing you can say is that, okay, this was there to begin with. The universe started with more baryons than antibaryons, or more quarks than antiquarks, and that has remained. Okay. But we would like to see if there is a better explanation of why this is the case, right? Why there are more baryons and antibaryons. The second point is that even if the universe started with, say, more baryons and antibaryons, right? Let's take it as a possibility. Okay. If you believe in inflation, right, and we discuss, okay, in the GR course we had discussed some aspect of inflation. We'll do it later in this course. But inflation basically postulates that in some time in the early history of the universe, it went a rapid expansion, right, exponential expansion. Okay. This was proposed to solve the horizon problem, and we'll review it later when we discuss inflation. Okay. But the net point is that this explosion increased the scale factor by at least e to the 60 times. Okay. So inflation increases lambda by e to the 60 times, at least e to the 60 times. Okay, this is needed if you want to use inflation to solve the horizon problem. Okay, and again this is something that we'll review later. Okay. But assuming this is the case, okay, we see that all the densities get diluted by e to the minus 180. Right, because density falls over 1 over lambda cube. Right, so if the universe expands by e to the 60 times, then the densities get diluted by e to the minus 180, right, which basically means that it's, even if we started with more baryons and antibaryons, okay, after inflation that effect is totally wiped out, right, because the densities become very, very small. So it's as if we had started with no baryons and antibaryons, right, no excess conserved charge. So if we believe in inflation, then even if we start with more baryons and antibaryons, it doesn't help, right? The baryon asymmetry has to be produced after inflation. Okay. So the baryon asymmetry has to be produced after inflation. If the scale factor increases by 2 to the 60 times, right, we know that conserved densities fall off as 1 over lambda cube, right? So if lambda gets increases by 2 to the 60 times, then the densities will fall by 2 to the minus 180, right? That's the dilution.
And then if we start with more baryons than antibaryons,
then the number will get multiplied by 2 to the minus 180.
Both the numbers.
Yes. So the asymmetry will be very, very small, right? So it will not be able to explain what we see in the present universe.
The conserved charge will be very small.
Exactly. The conserved charge will be very small. Yeah, today we know that NB minus NB bar, right, that ratio to the number of photons is 1 in 10 to the 10. Right? It's not a small number like e to the minus 180. Pardon? Well, then you have to explain, I mean, again, okay, you can say, okay, you can always start with very, very high baryon density, but then what will happen is that then the evolution of the universe will be quite different. right? Because the baryon has to be produced using quarks, right? If you pack such high density of quarks, then the matter density will become so high, then you cannot use the standard FRW solution anymore, right? You have to take that into account. So it is very hard to start with such a high density that after inflation, it will still be appreciable, right? And which can explain what we see today. Okay. So basically the idea is that inflation erases anything that happened in the past, right? You basically start with a universe that is flat and it's devoid of all matter, right? Except, as you will see, there is a cosmological constant which eventually generates everything else. But clearly the point is, once you have an expansion of this kind, right, then first of all you see radiation falls off as 1 over lambda cube, lambda to the 4, right, radiation energy density. So that will fall off even faster, e to the minus 240. But any matter density that was there, right, in X is baryon density, that will get diluted by e to the minus 180. Okay. So this is the reason why the baryon asymmetry has to be produced after inflation. And the question that you want to address is how. Okay, how can we produce baryon asymmetry? Okay. Now, before we discuss the details, okay, let me write down what are called Sakharov's conditions. Sakharov essentially wrote down 3 conditions that must be satisfied in order to produce baryon asymmetry, okay, or any asymmetry, okay, anything that was not there to begin with. If you want to produce it, okay, he wrote down the 3 conditions that need to be satisfied. So the first is that the microscopic theory must have B violation. That if the microscopic theory doesn't have a baryon number violating process, then clearly you cannot produce baryon number. Right? There should be some thing that allows it to produce baryon number that which produces more baryons and antibaryons and or vice versa. Is this point clear? Right? This should be obvious, right? Because if the macroscopic theory cannot produce baryons, then whatever you do, if you start with 0 baryon number, the baryon number will remain 0. Right? Which means the baryon number shouldn't be conserved. Right? If the baryon number is conserved, then microscopic theory cannot produce baryon number. That's all that this means. So shouldn't be conserved. The second criteria is that the theory must violate C and CP symmetry, where C is charge conjugation and P is parity. This is slightly less intuitive, but it can also be argued without too much effort, okay, and that goes as following. That imagine that there is some process, okay, which produces more baryons and antibaryons, right? Because that's what it need, right? It should produce more baryons and antibaryons. Then if C is a symmetry, right, then its charge conjugate process, right, what it will do is that it will convert all the particles to antiparticles. Okay, it will have exactly the same cross section, right, same rate. So charge conjugate process will produce more antibaryons than baryons. Okay. And if the initial configuration was invariant under charge conjugation, right, which is what would have been, because initially you say that everything is so diluted that it's as if you are starting from nothing. Okay, all conserved charges are 0, right? So then, of course, that's invariant under charge conjugation. Then, any process that produces more baryons, right, has a counter process that produces more antibaryons, right? The charge conjugate process. And so the net effect will be null, right? The number of baryons that is produced versus number of antibaryons that will be produced will be the same, because any process that produces more B that more B than B bar has charge conjugate process that produces more B bar than B. Okay. So the net effect is null. Another way of saying this is that if the universe starts with a charge conjugate invariant state, right, or a density matrix, then if the Hamiltonian is charge conjugate invariant, if it commutes with charge conjugation, then under Hamiltonian evolution, the density matrix will still be charge conjugate invariant. And if the charge conjugate invariance means that it will have equal number of particles and antiparticles, and hence no excess baryons. Is this point clear? Right? A charge conjugate invariant state will evolve into a charge conjugate invariant state, right? And hence there will be no excess baryon compared to antibaryon, because asymmetric universe is not invariant under charge conjugation, right? If we take our universe and charge conjugate, you will get more protons than antiprotons. Sorry, more antiprotons than protons, right? So it's certainly not invariant under charge conjugation.
This is so C violation is needed because we want to produce more baryons.
Exactly.
More baryons than antibaryons, or vice versa.
Vice versa, yes.
Maybe parity violation is needed for.
Yeah, parity violation is not needed. CP violation is needed.
Oh, CP.
Right? Why CP? Because CP has the same effect, right? CP, what it does is it charge conjugates, but it also changes the parity of the particle. Right? It will still convert particles to antiparticles, right? But with opposite parity. Right? So the same argument for CP.
If second this C and CP doesn't get violated, then D violation is it possible? First one.
It is possible in principle, yes. Right? You can have C and CP conserving process, but baryon number is symmetry is not there.
Totally different group.
Yeah, it's a different group altogether, right? Baryon number is a continuous symmetry. It has a continuous symmetry. It's baryon number is, you can think of it as a U1 symmetry, right? I'll write down the baryon number transformation laws.
Okay.
Right? It is certainly possible to have C and CP violation without baryon number. Okay, maybe I can write down baryon number baryon transformation law here, right? So baryon number is associated with U1 symmetry. Okay. And the point is that Q, every quark carries charge 1/3. Q bar carries B equal to minus 1/3. Everything else carries 0. Okay. So Q, the field goes to e to the I theta by 3 times Q. Q bar goes to e to the minus I theta by 3 Q bar, and everything else is neutral. Okay, so if the Lagrangian has terms that doesn't respect this symmetry, then it will be violated. Is this clear? Okay. Now, the reason that one mentions CP separately is because often we encounter theories where C is broken, but CP is present. Even those theories are allowed, right? For example, if we just look at the standard model, right? I mean, you don't have to write the Lagrangian, right? We know the standard model has left-handed neutrino and right-handed antineutrino. Okay, so take the neutrino and take its charge conjugate. Okay? Take a left-handed neutrino, take its charge conjugate. It will become a left-handed antineutrino, right? Which is not even there in the theory. So obviously C is not a symmetry, right? But under CP, a left-handed neutrino goes over to right-handed antineutrino, right? So that particle is there, right? So it's not obviously violated CP. Right? And in fact, one can show that in the standard model, if two generations of fermions have CP invariance. But if we have standard model with three generations of fermions, then it is possible to write down terms in the Lagrangian that violate CP. Okay, so CP is more stringent. That C is often violated. Right? To violate CP, you have to do more work in the Lagrangian. Right? That's why one adds the CP as a separate condition. Is this point clear? The third condition is the least intuitive, and that is that the universe must be out of thermal equilibrium during excess baryon production. Why is it needed? Because if it's not violated, right, then take a state, a process, its CP transform, right, will, if a given process generates more B than anti-B, then its CP transform will produce more anti-B than B. Because CP also charge conjugates, right? It also transforms, it reverses its parity, right? But if a given process produces more baryon, its CP conjugate process will produce more antibaryons. Okay? It's basically the same argument, right? You just replace C by CP in all the arguments that I gave, right? You can say if the density matrix is
Parity come here in B
it reverses the helicity of the particle, right? It doesn't come in the argument, right? But it's written separately because often theories violate C, but they preserve CP. Yeah, that's why CP is written as a separate condition. That it should violate C as well as CP, right? Because if you violate C and not CP, it's not good enough.
So when you say often, because I know only this neutrino.
Well, standard, that's our world, right? I mean, the standard model has that property. Because the point is, under C, a particle will go to its antiparticle with the same parity, right? And that often you can violate, right? If that particle doesn't exist. Right? Now, what I can say, can we start with a neutrino, okay, and say there is no antineutrino at all of any parity? Right? Is that possible? Right? Then both will be violated clearly, right? But then something else will be violated, that is CPT, right? CPT we cannot violate in a local theory, right? There is a general CPT theorem, right, which says that you cannot violate CPT in a local quantum field theory. So CPT is always a symmetry. Okay? So given that, we can ask then now, right, what about this argument, right? Can we apply CPT to argue that there will be equal number of baryons and antibaryons, right? Or that if you start with a CPT invariant state, it will evolve to CPT invariant state. The reason that CPT doesn't work, okay, is because we are working in an expanding universe, right? And the time reversal symmetry is already broken by the background. Right? So time reversal symmetry is not a symmetry of the problem that you are dealing with. Right? So even though CPT is a symmetry, we cannot use it, along the same line of argument. Is this clear?
Then CPT is a symmetry.
Yes, CPT is always a symmetry of the theory, not necessarily the background. Right? Here the background breaks CPT. Right? And okay, I mean intuitively also you can see, right? What will CPT tell you? That suppose a given process produces more baryon than antibaryon, right? Then the reverse process, right, will go in backward in time. Right? So in the early there will be more antibaryons than baryons, right? But which is the same thing. So CPT you cannot use in this argument.
But this must violate C and CP. I mean, isn't violation of C enough to generate a symmetry?
Yes, it is. No, it is not enough. I mean, violation of C is necessary.
Oh, yeah, necessary.
Yeah, but suppose if there is a theory which preserves C.
Then we will need CP.
Then we, yeah. Okay, I mean, no, sorry. Suppose there is a theory which violates C. Okay, so then it's possible to have baryon number violation, right? But if it preserves CP, then again it's not possible, right? It becomes, so the condition is more stringent, right? You have to violate both C and CP. See, all these conditions have to be satisfied, right? So I could have written it as 4 conditions. It has to violate C, it has to violate CP, okay, and it has to violate B, and finally it has to happen out of equilibrium.
What I am asking is why violating C is not enough? Just it should be enough.
Well, these are all sufficient conditions, not necessary. Sorry, these are not necessary conditions, not sufficient. Right? So violation of C is a necessary condition.
And then we need CP as well.
Yeah, we need violation of CP is also a necessary condition.
There is an and.
Yes. So that's why, okay, if I write as 2A, I write CP. 2A. The theory must violate CP. That you have to satisfy first condition, second condition, that condition 2A, and condition 3. Right? These are necessary conditions. Doesn't mean that if you do all that, you will actually get baryon number violation, right? That you have to check by doing explicit calculation. But if you don't satisfy any of these, then there is no hope of getting baryon number violation, right? That's what it says. So unless your theory satisfies all these conditions, you don't even have to look at that theory whether it can produce baryon number or not, right? You know from before that it can never produce baryon number.
So it's like even if baryon number violation is there, C violation is there, and that condition is satisfied. If CP violation is not there, then there can be some process which will make it
equal. Exactly. Right? There will be some process that will make it equal, right? Because you cannot start with a CP invariant state and produce CP non-invariance, right? Even if you satisfy all the other conditions. So these are all necessary conditions for baryon number violation.
What you said about time reversal?
Yeah, so CPT, you could have asked, I mean, can we use a similar argument for CPT, with CPT, right? Because CPT, you know, is always a symmetry, right? But T in this case is broken by the background, right? Because the universe is expanding. So what it will say is that if there is excess baryon produced in an expanding universe, then there will be excess antibaryon produced in the contracting universe. Right? That's what CPT will tell you. Right? But that's okay with us, right? We know that we are in an expanding universe and not in a contracting universe. Right? CPT is preserved. The theory, microscopic theory has CPT, but the fact that the microscopic theory has CPT invariance doesn't mean that rules out baryon number production, because time reversal invariance is broken anyway by the background. So CPT, so the background is not CPT invariant, even if the microscopic theory has CPT invariance. Yeah, the solution that you are considering, FRW solution, that explicitly breaks CPT. right? Because it breaks time reversal invariance. Is that point clear?
So, I mean, is it same as saying, I mean, because we know that because we have a preferred choice of direction in time,
Yes,
that's why like violating CPT cannot help us,
exactly,
right?
exactly.
For the purpose.
Yeah, that CPT is, I mean, that CPT may be a theory, a symmetry of the microscopic theory, right? But it's not a symmetry of the background, right? So having the existence of CPT is not going to help us ruling out baryon number violation. Right? It will only tell us that if excess baryon is produced in an expanding universe, then excess anti-baryon will be produced in a contracting universe.
Is it like saying CPT violation is like a trivial condition? Because CPT is already violated in
Exactly,
global
that's right.
case.
Yeah, CPT is already violated by the background.
Yeah. So CPT theorem, that is for the microscopic theory, not for the whole theory.
Exactly, microscopic theory, but see, a symmetry in the microscopic theory, right, doesn't mean that it has to be a symmetry of all background. Right? Imagine that you have a potential, right, which is symmetric, right? But you can choose to put a particle somewhere else, right, which breaks the symmetry. Right? Or I mean, another example is double L potential. Right? It may be symmetric around x equal to 0 with the two minimum at minus a and a. Right? But you can choose to put the particle at minimum a, right, where it breaks that symmetry. Right? So, but here in this case, the theory is invariant under x goes to minus x, but the background that you have chosen is not invariant under x goes to minus x.
Background is in this case same as saying the boundary condition.
Yeah, you can say something like boundary condition, right? Here you have started with the boundary condition where the universe started expanding.
How did he write these conditions beforehand? Like before knowing, did he write these conditions before knowing any process?
Yeah, I mean, he knew quantum field theory, of course, right? And the point is, now we are trying to look for a quantum field theory which satisfies these conditions, right? But so he wrote down these conditions so that it helps him search for which kind of quantum field theories could possibly produce baryon number violation. Yeah, so these are, I mean, conditions on the quantum field theory, underlying quantum field theory that can possibly give rise to baryon asymmetry. Okay, so now let me describe this third point, right? Why is it necessary? Okay. And for that, you have to recall the various formulae that we had for equilibrium statistical mechanics. So recall results from equilibrium statistical mechanics. So suppose you have a conserved charge. Okay, so let's say n alpha and n alpha bar are the number of particles and antiparticles of alpha f time. Okay. And then we wrote down, and suppose there are some conserved charges. N tilde L as sum over alpha Cl alpha times n alpha minus n alpha bar. Okay, so these are just constants. Okay, baryon number had been a conserved quantity, then this will be like 1/3 for quark and 0 for the rest. Okay, that's what I mean by, so these numbers are just numbers obtained in the microscopic theory. In that case, we introduce introduce chemical potential mu tilde L. Yeah, let's say L goes from 1 to K, 1 to L, capital L. And in the exponent of the partition function, we write sum over L mu tilde L NL n tilde L, right, which I can rewrite as sum over alpha mu alpha times n alpha minus n alpha bar where mu alpha is sum over L mu tilde L C L alpha. Okay, I hope you remember this formula that we wrote introduce chemical potential mu tilde L for every conserved charge. Those are the independent variables, right? And in terms of mu tilde L, we arrived at this mu alphas given here because that's what you can rewrite this in terms of this. And once we know the mu alphas, right, we can write down the number densities. So the formula for the number densities is n alpha as g alpha over 2 pi integral okay, this minus is for the bosons and plus is for the fermions, right? But this was the formula for n alpha, and then n alpha bar was g alpha over 2 pi okay. The only thing that changes is that the minus mu alpha becomes plus mu alpha here. E of k is the formula for the energy of a particle carrying momentum k, right? So the relativistic formula is square root of m alpha square plus k square, right? That's what E of k was. Maybe I can write E alpha of k because this depends on the energy of the particle, which particle it is, right? The formula involves m alpha square plus k square. And then we write the expression for the conserved charge densities. N tilde L is, we use this formula, right? Sum over alpha CL alpha times N alpha minus N alpha bar. And then for N alpha and N alpha bar, we substitute from here. So this is given by sum over alpha CL alpha G alpha over 2 pi integral 0 to infinity k square dk, and then we have 1 over Is this clear? And let me write this formula again. So mu alpha is given by this formula over here, sum over L, mu tilde L, CL alpha. And this equation is valid for L equal to 1 to L. Right? The number of for every conserved charge you have n tilde L, right? That is conserved. That means n tilde L m lambda cube doesn't change with time. And we can apply it for all the capital L number of conserved charges. So this gives you capital L equations for capital L unknowns n tilde L are given. N tilde L given as boundary condition. Right? These are the conserved charge density. So n tilde lambda cube is fixed. Right? It doesn't change as a function of time. So that's to be given some time. Right? And in particular, if we believe in inflation, then all the n tilde L's must be 0. Right? Because inflation basically diluted all conserved charges. So we can take, so the natural boundary condition is all the n tilde L's are 0. We are trying to prove why statistic out of equilibrium is necessary. Right? So right now we are saying what is the consequence of equilibrium. Right? Imagine that you have equilibrium. Right? Then we are just using these various formulae, right, to write down an equation that determines the mu or mu tilde alphas, mu tilde L's in terms of the L tilde L's. Right? So the idea is that n tilde L's will be given to you, and mu tilde L's is something you have to calculate.
But we have not given any input of the process which will produce baryon symmetry.
For equilibrium, it doesn't matter. We are just applying equilibrium formulation. Right? That process is not important for this, because you are trying to understand this last condition. Right? That you shouldn't use equilibrium. That you cannot, the baryon number production cannot happen in equilibrium. Okay? Irrespective of whether everything else may be violated. Right? C, Cp may be violated, baryon number may be violated, but if you have equilibrium, we will try to argue that you cannot produce baryon number. Right? So for equilibrium, we can just use this formula.
First and second condition are not included in this.
First and second condition?
There is no baryon conservation.
Yes.
Isn't it included in this only? Like there is no conservation.
Well, it is included in this. I am assuming, okay, yeah. I mean, otherwise baryon number will be also part of the conservation laws. Right? See, if the baryon number is conserved, then of course you can never generate baryon number. Right? So, see, these are all necessary conditions. Right? We are saying even if the first, second and third condition are satisfied, you need this one. Right? The out of equilibrium. The first number condition satisfied means baryon number is violated. Second condition satisfied means C is violated. Third condition means Cp is violated. Right? Even then, we need this.
But can it happen that they mutually contradict each other?
Doesn't matter, then you can never produce baryon number. If you can argue that there is no theory where all four are satisfied, then you can never produce baryon number in the universe. Right? Because these are all necessary conditions. Right? First condition is necessary, you have to violate baryon number. Second condition is necessary, you have to violate C. Third condition is necessary, you have to violate Cp. And even if you do all that, the fourth condition is necessary, that you have to violate, you have to be out of equilibrium, right, which is what we are trying to argue.
Conserved charge taken 0.
Hmm.
This is after inflation. Now suppose after inflation there is a process which can generate more baryons than antibaryons.
Yes.
Can you take this conserved charge to be 0 then?
Oh, in a L tilde by definition are the conserved charges. If it can produce more baryon than antibaryon, then it's not a conserved charge, right? We are applying this on the conserved charges only.
But doesn't that mean we are not considering a process which more baryons than antibaryons?
No, that's included in this. We are not including baryon number as part of the conserved charge, right? Right? I mean, we have not included. If you include the baryon number as part of the conserved charge, right? And then if you assume that that it's always conserved, right? Then you can never produce baryon number. Then already the first condition is not satisfied, right? So you don't have to do anything else. If the first condition is not satisfied, baryon number is not produced. Okay. So you have to look at the logic that each of these are necessary conditions for producing baryon number, not sufficient. Right? You have to satisfy all these four conditions to be able to produce baryon number. Okay. If the first condition is violated, then baryon number is one of the conserved charges. Then if you start from baryon number equal to 0, it will always remain 0, right? There's nothing to argue. Yes.
We are considering some conserved, not baryon number.
Not baryon now.
After doing this, we will show that baryon number will also be conserved if it is in equilibrium.
The baryon number will be 0.
Will be 0.
Yeah, not conserved, it will be 0. Okay, that distinction will be important here. Not now, later. Is this point clear?
So if it's 0, then it is conserved, and this assumption that we have taken that baryon number is not conserved will be valid.
Exactly, yeah. Yeah. So the point is this argument, so this last argument, right? We don't care how many baryon number was produced at the beginning. Right? All we care about is the conserved charges. That all the conserved charges were nearly 0. Right? Because baryon numbers may be produced, not produced in the, I mean, if the baryon number is not conserved, right? Then the fact that initially there was no baryon number, right, doesn't mean that later on there will be no baryon number, right? And we are not using that anywhere in this argument, right? This argument is based, so far, based only on the conserved charges. Is this point clear? Right, so the baryon number is not included in one of these capital L, right? Because if it was included in one of the capital L, then the first condition itself is violated. Right? Baryon number is conserved, so you cannot produce it.
So our assumption is just that N tilde and are 0 initially.
Exactly, right?
We'll
And
show
hence,
that even if baryon number violation and CP.
so N tilde L's of course are not changing. N tilde L's are conserved, right? So N tilde L lambda cube remains constant, right? It may be some electric charge. Electric charge you know is conserved, right? And so one of the N tilde L's could be just the electric charge density. Right? And we are saying that if it starts with 0 electric charge density initially, it will always remain 0. Okay, so the idea is that you want to solve for the equation N tilde L equal to 0. Okay. This tells us, given N tilde L, that there are equal number of variables than equations. Mu tilde L's are the unknown variables. Right? So once you supply the N tilde L's, there are capital L equations for capital L unknowns, and you can solve it. Right? And this is something that I will not try to show here, but for ideal gas, the solution is unique. Okay, we are going to use it that you can, given the N tilde L's, you can fix mu's uniquely, the mu tilde L's. Okay, now suppose N tilde L equal to 0. Then what will be the solution for the mu tilde L's? Assuming it's unique, right? Can you think of a simple solution for the mu tilde L's that will do the job?
Both of them are alpha is 0.
Pardon? Yeah, so if all the mu tilde L's are 0, right, then mu alpha will be 0 by this formula, right, and then these two terms will exactly cancel each other, right, and that will satisfy that these are all 0. So if n tilde L equal to 0, then the solution is mu tilde L equal to 0 for all L. Is this clear?
To become only solution.
Yeah, we can argue that this will be the only solution, but I am not going to prove this here. Okay, so if the mu tilde L's are 0, then this equation tells us that mu alpha is 0 for all alpha. And hence, if you look at this formula, n alpha equal to n alpha bar for all alpha. Right, that comes from these two equations. Is this clear? Now let's look at the formula for the baryon number. This will be some linear combination. These are not C. Let me call it something else. E B alpha these are some constants. Right? For example, for the standard model that I wrote down, it will be quark carries 1/3, anti-quarks carry minus 1/3, right? So EB alpha will be 1/3 for the quarks and 0 for everything else. Okay, but this will be a formula for the baryon number density. Is it clear? That the only thing that is I am using is that the particles and antiparticles have opposite baryon number. Right? That's always the case. Any charge that you define, right? The particles and antiparticles carry opposite charge. And now you see that because n alphas are all 0, this means that NB is 0. Is this point clear? So this argument, if you notice, I didn't assume that to begin with NB was 0. I only assumed that the conserved charges were 0. Right? So whether the baryon numbers are produced by some non-equilibrium process or not doesn't matter. Okay, we only assume that n tilde L's are 0. Just based on that, we reach the conclusion that mu tilde L's are 0, hence all the mu alphas are 0, because mu alphas are not independent variables, right? Only mu tilde L's are independent variables. So once all the mu tilde L's are 0, mu alphas are 0, right? And that in turn means that the NB is 0.
What are E alpha B's?
Some constants. Like as I said, if you have the example that I gave for the standard model, right? This will be 1/3 for the quarks and 0 for everything else.
So everything else, everything will be annihilated and nothing will be.
Well, no excess, right? There can still be particles and antiparticles, right? But there will be no excess.
This is because of the erasure by the inflation. That boundary condition is set.
Yeah, because initially if you set all the conserved charges to 0, right? You can say inflation or you can say this is the natural boundary condition, right? If you have some conserved charges, why should you start with one excess, right? You want to generate all the things that you observe. So baryon number is apparently conserved from the low energy viewpoint, right? But if you want to generate it, you need baryon number violation, right? That's the first criterion. But then you also need all of these. Right? C violation, CP violation, and then the process has to produce baryons out of equilibrium. Is this point clear? Now, standard model, does standard model satisfy all this? So, 2 is easy to understand. So, C violation, C and CP violation, indeed it does. Okay, standard model interactions do not conserve C and CP. Baryon number violation. Now, as we discussed, there is a symmetry, U1 symmetry, where each quark changes, picks up a phase, each anti-quarks pick up opposite phase, and everything else neutral. So, this is a symmetry of the Lagrangian. So, this would suggest that we can never violate baryon number within standard model itself, right? You have to go beyond the standard model to have baryon number violation. But it turns out that this symmetry is anomalous. Okay, I will not explain this in detail. This is a phenomenon in quantum field theory, that some of the classical symmetries may become non-symmetries once you take into account quantum effects, right? In particular, one loop effects in the quantum field theory, and it turns out that the baryon number current is like that. Okay, it's anomalous, so it's not conserved. Now, if it's not conserved, then that seems bad news for us, right? Because then what is happening to the protons, right? That why aren't they all decaying away? If the baryon number, if charge of course is conserved, right? But proton could decay into the positron plus something else, some neutral particle, for example, right? The reason that it doesn't happen is because the actual processes are highly suppressed. It's like e to the minus the rate had a is proportional to e to the minus 4 pi square over the weak interaction coupling constant square, and that's very, very tiny, right? If I remember correctly, it's something like 10 to the minus 1, 10 to the minus 160 or something. So even if these processes are possible, right, it's very, very slow. Okay, so it's as if these effects don't exist. Right, you don't, such slow rates will not affect anything. However, it turns out that even though the rates are slow at the kind of energies that we are interested, that we work with, like proton, for example, the proton, when you try to calculate if the proton can decay via these interactions, indeed it can decay, but the rate is very, very small. But at high temperature, this suppression goes away. And the reason is that the reason that it's so small, okay, is because there is some kind of tunneling that the theory has to perform to make use of this barrier number violation. And the tunneling probabilities are usually very small if the barrier height is high. Right? So it goes via tunneling. Okay, this rate goes via tunneling. I will not explain what it tunnels via. The tunnels to goes via tunneling. Okay, so it's like there is a periodic potential. Okay, and the theory has to tunnel from one to the other to make use of this barrier number violation, right? And this tunneling rate is very, very small because the barrier height is large. But as you increase the temperature, right, the energies that are available to the system becomes larger, the energy densities, right? At high temperature, you have high energy density. And you can see that just like tunneling, right? If you are sitting in the ground state, it's hard to tunnel in a quantum mechanical problem. But if you are having an energy of this magnitude, right, then you can smoothly go to the other side, right? The tunneling, there is a suppression due to tunneling. And this is what happens at high temperature. That at high temperature, the quantum field theory is able to make use of this tunneling effectively. Right? And hence, the fact that it was suppressed, it was so small at low temperature, right, it doesn't bother high temperature physics. Right? At high temperature, this rate is of order 1. Well, if this formula, right, is valid at low temperature, at 0 temperature, right? At high temperature, there is a different kind of solution that you have to do by tunneling. Right? So this formula is a tunneling formula, right? But tunneling is not relevant once you have energy above the barrier, right? So this, what you see in the exponent, right, is basically this integral of this E minus V dx, right? Which goes into the WQV expression for tunneling, for example. Okay. And that suppression is simply not there here. Instead of e to the minus something, it becomes exponential of an oscillatory function. Right here, so you don't see this effect. But the net upshot of this is that while the standard model barrier number violation is not possible at low energy, is very, very small at low energy, at high temperature, right? And the universe was at high temperature earlier, it could produce such tunneling effects, okay, with high rate, and hence it could possibly produce barrier number violation. And the barrier number violating processes in the standard model are not small at high temperature.
Where is this temperature information going into the Lagrangian? It is not right.
Well, you have to write some effective. Yeah, it's not direct. It's not, when you write down a usual quantum field theory Lagrangian, it's not going in, right? But you can write down some effective Lagrangian where it will go in, right? Or sometimes you can just do the calculation with the low energy Lagrangian, but take into account the effect of temperature differently.
Temperature is basically the kinetic energy of the incoming optical particles.
Well, it's kinetic energy of the of the fields, right? You can write down a partition function for the fields, right? Just like you do write down a partition function for a gas of particles, right? In fact, you have been assuming implicitly that we have a partition function of the fields, right? If you have a gas of partition function of photons, right? You can do that calculation as thinking of this as a collection of particles, but also as thinking of this as a collection of electromagnetic fields, right? So similarly, in a quantum field theory, the temperature information is in the calculation of the partition function of the electromagnetic field. Okay, so the upshot is that it is possible that standard model itself produce this baryon asymmetry, because first condition also is satisfied. So first, second and the 2a all are satisfied. Question is, what about the third one? Was it out of equilibrium? Was during this process, right? Could you have gone out of equilibrium? And this question is crucial, right? If you could go out of equilibrium, then the standard model will produce baryons. Okay. But the reverse side of the story is that if you were in equilibrium, right? Suppose you find that you are in equilibrium, then any baryon asymmetry that was produced earlier will be wiped out by the standard model, by this argument, right? Because this argument didn't depend on the fact that there are some baryon number produced earlier, right? So if the system was in equilibrium at the time when the baryon number violation was appreciable, then it will just wipe out any baryon number asymmetry that might have been produced earlier. So it doesn't matter what happened earlier, standard model determines whether the baryon asymmetry is there or not. And we will see next time that the system was actually in equilibrium at that temperature. Right? This is something, of course, you know the standard model Lagrangian, so you can figure out whether the system was in equilibrium or not. And I'll say a few more details about what you need to do to check this. But the upshot is that the system was in equilibrium, and hence you will conclude that any baryon asymmetry that was produced in the past will be wiped out. And this will be a naive conclusion, but we will see that there is a way to get around it. Okay, and that's what we will focus on next time.
Given that rate, some rate will be there at high temperature to turn it.
Yes.
That rate will it not be same for both going from baryon to some or anti-baryon?
Yes, but it need not be the same because C and Cp are violated, right? C and Cp are violated, baryon number is violated, right? And if you are out of equilibrium, then you have satisfied all the conditions. You still have to do the work to calculate whether how much baryon asymmetry it will produce. Okay? But at least you know that all the conditions are satisfied, right? That it is possible in principle to produce baryons. Okay, so I think today I'll stop here. We'll continue tomorrow, right? We'll explain what determines the nature of the whether it's in equilibrium or out of equilibrium, and then how to get around this problem that if it was in equilibrium, then the baryon number just gets wiped out, right? Whatever baryon number was produced doesn't remain anymore.
High temperature, roughly how much?
Standard model phase transition, 250 GeV, right? That's the vacuum expression value of the Higgs, right? That is the kind of temperature you are talking about here. Right? Below that, the suppression starts taking over.
Actually, I was thinking cover.
Yeah, but if you know things. Yeah, you just send me some topic, right? Then we can discuss, right? What? Yeah, I think it should be okay. You just send me whichever topic.